All right, next we're going to be looking at survival needs. And that's because humans need several factors for survival that have to be in the appropriate amounts. Too much or too little of any of these survival needs, it's not going to work out well for us. First and foremost, nutrients. These are chemicals for energy and cell building. Carbs, proteins, lipids, vitamins, minerals, all those are included. But too many carbs, too many proteins, too much fat, especially too many of certain vitamins and minerals, can be dangerous and can cause certain types of conditions. So we need them within appropriate amounts. And you're going to see that as a theme again for these survival needs. The second survival need is oxygen. It's required for all chemical reactions and the release of energy from food. Oxygen actually powers the breakdown of glucose to produce ATP, which is cellular energy. Water is very important. It's probably one of the most important non-organic compounds that there is. About 60 to 80% of body weight is water, and it's required for chemical reactions. So no part of metabolism, no part of building processes or breakdown processes in the body happen without water because chemical reactions require watery or aqueous environments. Then temperature, too hot, too cold, not good, but it is important to maintain a stable body temperature at around 37 degrees Celsius. Processes of homeostasis that maintain dynamic ranges for internal conditions help maintain things like blood glucose and body temperature. And then, of course, atmospheric pressure, which may not have been one you thought about. This must be within an appropriate range for breathing and gas exchange in the lungs. If there wasn't pressure differences between the pressure in your lungs and the pressure outside around your body, which is atmospheric pressure, then we wouldn't be able to breathe. So all of these are things the body needs in order to survive, but not too much or too little, just the right amount. And I've mentioned a couple of times in the chapter 1 videos, homeostasis. So what is that? Well, it's the ability to maintain relatively stable internal conditions, even though the outside world changes continuously. So it's a dynamic state of equilibrium. What is meant by that is there's kind of a lower range and a higher range for a certain condition, whether it be blood sugar, temperature, heart rate, amount of nutrients, amount of waste. And the body is able to change and move between these lows and highs among this dynamic range to keep the internal conditions relatively stable. Now, oftentimes we'll say there's a set point, like body temperature being 37 degrees Celsius, but really there is a low and high scale. And as long as everything stays within that scale, we are in homeostasis. Moving out of homeostasis is considered a homeostatic imbalance, and that's oftentimes associated with disease or aging. Now, what maintains homeostasis so well in the human body is communication. Communication using the body's two communicating systems, the nervous system with its electrical impulses, and the endocrine system with its hormones that travel via the blood. We really don't want to see disturbance of homeostasis. We want to maintain stable blood sugar, stable amount of waste in the body, stable amount of nutrients, stable body temperatures. Because having a disturbance in homeostasis, having a homeostatic imbalance, increases risk of disease. A lot of aging is associated with disturbances in homeostasis, like allowing destructive positive feedback mechanisms to take over and build plaques, or cause atherosclerosis in the blood vessels, can lead to friction and stresses the heart, which can lead to heart failure. And one of the most common homeostatic imbalances that can be very hard to treat is the uncontrolled and unchecked growth of cells that happens as they experience multiple rounds of mutations that do just naturally happen in the human body. But these uncontrolled and unchecked growths of cells can lead to cancer. So when we talk about homeostasis, the basic definition is great, but how can we study it? Well, we can study it knowing the variables, the factors that we have to look at in order to look at homeostatic control. Homeostatic control of variables involves three components: the receptor that picks up on a stimulus, the control center, which is usually an endocrine gland or something in the nervous system, like the brain, and the effector. That's going to be where an output goes, and we're going to see those cells have an effect. Usually the effects are muscle contraction or gland secretion. So let's look a little bit closer at each one of those variables. We have the receptor, and it is really just a sensor. It's an input mechanism. It receives a stimulus, so it can respond to the stimulus. A stimulus is anything that can cause a change in the controlled variables. Once the receptor receives a stimulus, it then sends that information to the control center. The control center is determining a set point, an ideal condition, or within what range we want to control this stimulus. So it's going to analyze information, integrate it, put it together, and determine an appropriate response, an output. So once the control center receives an input, it analyzes and integrates, and then it sends out an appropriate response called an output that goes to the effector. The effector is the body's means for responding, for showing an effect in relationship to the output it received. So it provides a mean of response to the stimulus, it receives the output from the control center, and the response either reduces or undoes the original stimulus. That's a negative feedback mechanism, or enhances the original stimulus, which would be an example of a positive feedback mechanism. Most of the homeostatic mechanisms within the human body use negative feedback mechanisms, where if something increases, the response is to decrease it, or if something decreases, the response is to increase it. Negative feedback mechanisms undo or do the opposite in output what the stimulus initiated. So let's talk a little bit more about negative and positive feedback. So negative feedback is most common. It decreases or shuts off the stimulus to reduce intensity. Now, decrease is not always what happens, because if a decrease is the stimulus, the output and effect would be an increase. But negative feedback mechanisms basically make the original stimulus go away. If body temperature decreases, the body will respond in order to increase body temperature. If blood glucose levels decrease, the body will respond to increase blood glucose levels. If heart rate goes up, the body will respond to bring it down, and vice versa. Negative feedback is going to be the opposite in output and effect from the original stimulus. Whereas positive feedback is going to enhance or exaggerate or amplify the original stimulus. If this was how the body usually worked, if it usually used positive feedback mechanisms, blood glucose would go up, and then the body would make it continue to go up. Heart rate would go up, and the body would make heart rate continue to go up. You would see an enhancement and basically an exaggeration of that original stimulus. So this is not used a lot. The body does use positive feedback occasionally, like for blood clotting or labor in women. But positive feedback is usually more associated with homeostatic imbalances and disease. When the body does intentionally use positive feedback mechanisms, they are very closely controlled. And as soon as the original stimulus disappears, the positive feedback mechanism shuts down. Negative feedback mechanisms also shut down, but they are, you could say, healthier for the human body, or less dangerous is probably a better term for a negative feedback system. Because once the original stimulus has been turned off, there's nothing to keep activating the negative feedback mechanism. So it's less likely to get out of control because the local regulation breaks down. All right, negative feedback, definitely the most used feedback mechanism in the body. We want to make that original stimulus go away. We want to do the opposite of it as our effect or response. And many of the effects are going to be gland secretion of a hormone or some type of solution, or muscle contraction. Regulating body temperature oftentimes is done by small muscle contractions to warm the body, shivering, or secretion of sweat to cool the body. And that's mainly a nervous system mechanism, so it's going to have the nervous system as its control center. The regulation of blood glucose by insulin uses the endocrine system as its control system, because it's going to communicate a stimulus, which is an increase in blood glucose, to the pancreas, and the pancreas will produce insulin as a result, which will cause sugar to go into cells and out of the blood, and that will bring down blood glucose levels. So it all depends on what negative feedback mechanism we're looking at. That kind of changes what effects and control centers we're talking about. So let's look at a closer example. So if receptors sense increased blood glucose, so we have extra blood sugar in the blood, The pancreas is the control center, which is a part of the endocrine system. It's going to secrete insulin to the blood. That insulin causes body cells, which act as the effectors, to decrease blood glucose levels because the body cells are taking in that extra sugar, meaning there's less sugar now in the blood, and that will decrease blood glucose. So that's just one example of a negative feedback mechanism. And here's a way you can visualize feedback mechanisms. So here we have a stimulus that is a signal that is going to be picked up by a receptor. That receptor then will communicate an input to a control center, and that control center will analyze and integrate and decide on an output that it'll then send to an effector. The effector is responsible for the response. It may contract, it may secrete. Those are the general effects. A lot of body cells are the effector, whether it be muscle or glands. You're also seeing two other terms here that we haven't yet seen or talked about: the afferent pathway with an A and the efferent pathway with an E. An afferent pathway is a pathway that heads towards a control center, especially if it's the nervous system. A way to remember that is afferent signals or afferent pathways arrive at the control center. Efferent pathways carry the output, so they move away from the control center. So efferent signals exit or move away from the control center. Let's look at another negative feedback mechanism. We're going to look at two different versions of maintaining body temperature. All right, so I'm going to start in the middle where we see an initial imbalance because body temperature rises. That's going to send a signal to thermoreceptors in your skin. Those temperature-sensitive cells in the skin and brain are then going to send signals to the brain via afferent pathways. And the brain is going to realize, hey, the body temperature is not quite correct. We need to bring down, in this case, body temperature, and they'll send out an output to effectors. In this case, the effector is glands, sweat glands specifically. And when you sweat, that sweat, which is very watery, absorbs heat. And when it evaporates off your body, it takes that heat with it. So in effect, the sweat glands will allow for the evaporation of sweat and the body temperature to fall. And that should bring us back to balance. You could also have the opposite happen. If the stimulus is cold and body temperature is falling, those same temperature-sensitive receptors in the skin will send signals to the brain. The brain will then cause skeletal muscles as the effector cells to contract, and that contraction produces heat as a byproduct of contraction, and that can warm the body or respond in a rise in body temperature. That should bring you back to a balance. So what we're seeing here is temperature receptors communicating to the nervous system and sending a signal then to an effector, whether it be a gland or muscle. Again, those are common effectors because they can do something. They can secrete or they can contract. But let's not forget positive feedback. Let's talk about what it does. Let's look at a couple of the local examples. And this again is going to respond by enhancing or exaggerating, really amplifying the original stimulus. Cascade, amplifying effect, common terms to talk about a positive feedback mechanism. Very infrequently used. Some examples that we have are the enhancement of labor contractions by oxytocin, and that initial stimulus of pressure and hormone release of oxytocin cuts off immediately after the baby is born. And then you have platelet plug formation that has its stimulus immediately stop after we form a platelet plug. Now we're going to look at a platelet plug formation, which is a positive feedback cycle. What we're seeing here is a tear in a blood vessel. So the blood vessel is bleeding from the inside out. What this does is it allows chemicals inside of the blood to visualize collagen fibers on the outside of the blood vessel. That is the stimulus that is needed to make platelets in the blood sticky. So they're sticky and they start to stick to the tear. At the same time, they start releasing chemicals that make even more platelets sticky and make them release chemicals. And so you'll have this constant amplifying, cascading event of platelets becoming sticky and sticking, making other platelets sticky by releasing chemicals and making them release their chemicals to make other platelets sticky. And you can see how that just continues and continues and continues until you fully form what's called a platelet plug. Now we've gotten rid of the original stimulus. When we had a break and tear in the blood vessel, inside chemicals could see the collagen on the outside of the blood vessel. If we have a fully formed platelet plug, inside chemicals cannot see the collagen on the outside of the blood vessel. So that shuts down the positive feedback cycle. So this is actually helpful for blood clotting, but it has to be closely controlled. Out of control blood clotting can be very dangerous and lead to things like a pulmonary or cerebral embolism. So we want to maintain homeostasis. We don't want to be in an imbalance. We want to use negative feedback mechanisms. So we have kind of this interrelationship among the receptors, the control center, the effectors, all working together to regulate events or factors that are out of balance to make sure we maintain homeostasis. Homeostasis is essential for the human body to function. We need to maintain stable internal conditions, regardless what's going on inside or outside of the body. So the body needs to be able to respond using these variables. Again, a receptor, a control center, and an effector. So that was a quick look at homeostasis, and now we're going to finally get into the language of anatomy. So that's going to be all in the next video.